So polynomial, poly means many, nomials means terms. So that's what that says right there, polynomials. And there's multiple terms in there. And the terms always have to have a positive integer value for the exponent. Okay? I'm never going to try to trick you with that by like giving you like a fraction one or something like that. For this unit, you'll always get like positive ones like this. Not negative. You can't have anything on the bottom either with a variable. Okay, if there's an x on the bottom, you can't have that. Okay, but again, I'm not going to try to trick you on that and go, ooh, I'm going to put one that's not a polynomial and see what they do. That's going to be part of a different unit where there's going to be x's on the bottom, but we don't have to worry about that for this one. Okay, here's an example of a polynomial. If you notice, it is smooth and continuous. There's no holes, jumps, or gaps. If you drew this graph out, you can draw it without lifting your pencil off the paper. Okay, it's one of the things with polynomials is they are smooth and they're continuous. Okay. You're always going to see things like this with polynomials, whether it looks like this or it goes up like this. Sometimes it'll be the opposite of that where it's pointed down. But more often than not, it's just going to be some curve like this, smooth curve. There's a term called degree of polynomial, and the degree just means the largest exponent, like the largest power you have. Okay, in this case, the power is 3, so the degree is 3. Okay. That's important to write down just in case like you're on a test and it's one of the questions is going to say, what's the degree of the polynomial? And you're going to go, hey, what's the degree again? And that's where you would want to look in your notes and you go, oh, degree is just the largest exponent we have. Okay. There is an exponent that's smaller than 3, like a 1 right here. It's x to the first power right here, but we want the largest, and the largest is the degree. Okay. All right. The reason why the degree is important is because it dictates what the graph looks like more than anything else because it's the biggest power. So that's what we call it. That's why it's an important concept to study for the degree. It dictates what the graph looks like more than anything else. And to kind of show you that, let's open up Desmos here just so I can show you an example. So like say I had something that was like y equals 4x to the third. Okay, it looks like this. Okay. But if I add like other stuff to it, like that minus x, you'll notice it still more or less looks like that original where it was just 4x to the third. Okay, it gave it a little bit more character, I guess, here. But for the most part, it's still doing the same thing. It's going to the same spot. In fact, if you zoom out, they more or less look the same. Okay, it's only when you actually like zoom in that it's not. So for really huge numbers, they're basically the same. That's why the degree is so important. It doesn't matter if you add, you know, let's see, if you make this a squared, okay? If you zoom in, it definitely looks different. You can see it looks different. But again, as soon as you zoom out, they just start becoming the same. That's why that power is important. The degree, the highest power is what's the most important. I can add more stuff at the end of this, plus 3x. And again, if I zoomed in, you can see that it's different. But as soon as I start zooming out, it's more or less overlaps. So again, that degree dictates what the graph looks like overall. All right, that's kind of what I was talking about there. So largest exponent. Standard form is what you're going to see all of these in every time. It's going to go from the highest power to the lowest power. I'm not going to try to trick you with that. So just know that. I won't try to trick you. You don't really need to worry about standard form as like a term to remember. Even degree polynomials always are symmetrical. Okay, there's some axis of symmetry. I shouldn't say that. Really, the ends have symmetry. Okay, it's not just the axis of symmetry, but like the ends either like go up like this or they go down like this. The ends match essentially. Okay, so doesn't matter what it is. I kind of showed you this yesterday, but if here's x squared. Here's x to the 4th, okay? Here's x to the 6th. Now you can see they're all doing this. They're all going up at the ends. I can make these all negative where they both go down at the ends, but the main thing is the ends match. If the ends match where they're going, then it's going to be an even function if it's a polynomial, okay? Even if I add like an x here, let's get rid of these. Even if I add an x, you'll still notice because the highest power is even, there's going to be some kind of symmetry to it at the ends. If I put a 4 here, now it's not really symmetry here, but the ends are symmetrical. So if I zoom out enough, it starts to look pretty symmetrical. Okay. You lose kind of the details when you zoom out and it looks symmetrical. Okay. It doesn't matter what I put in here too. If it was like, you know, to the third or something like that. If I zoomed in, you'd see that it's definitely not symmetrical, but the ends go in the same spot. That's the main thing, where the ends are going. Okay, I don't need that anymore. Okay, that's even degree. There are going to be certain questions where I give you a graph that looks like this, and I say, is this graph an even degree or an odd degree? And you should be able to say, oh, the ends are going in the same spot, it's even. Okay? If the ends aren't going in the same spot, like say it was something like this, oops, say it was something like this, you should say that that's odd because they're not going in the same spot. One's going up, the other one's going down. Okay, if they're both going up and both going down at the ends, then it's even. Okay. Any questions about what I'm doing? I know this seems like zookeeping with graphs essentially, but it kind of is. Representing everyone. Okay. Odd degrees, I already kind of talked about this. They go in opposite directions at the ends. Okay. All right. Relative extrema, also known as turning points, or I call them turns sometimes. If you ever want to figure out the degree or the lowest possible degree for a polynomial, you can just count the turns. However many turns it has, that's the lowest possible degree that it has. Okay. For example, and they have to add 1 to it. I forgot to mention that. So right here, there's 1 turn, 2 turns, and 3 turns. So because there's 3 turns, you add 1 to it to get the 4. Okay, so then you can say that it's a degree of 4. Okay, there are some times where it's a degree of 4, but there's only 1 turn. Okay, so you could have less, and that's kind of what it says there. A polynomial of degree 4 can have 3 turns, or it can have less than 3 turns. Okay, it has to have at least 1. It could have, you know, it could have 2, it could have 3, it could have 1, but it can't have 0 because then it wouldn't work. But the most is 3. Okay, it cannot have 4. That's impossible. Okay. Okay, the fundamental theorem of algebra states that whatever the degree is, so we're going back to that degree thing right here. Degree is the highest exponent. This tells you how many answers there are. This one, if you solve this out, there would be 3 answers to it. Okay, that's called the fundamental theorem of algebra. Any polynomial of degree n has n roots. Okay, but you may have to use complex numbers. Those are the imaginary numbers. We're going to get into that in the next section, 2.2. I'm not really so worried about it in 2.1, just because I just want to focus on the graph and understanding what all this stuff means. Okay. A root or a 0 is where the polynomial is equal to 0. Okay, you should know this already. So this right here is considered a root. That's a root. That's a root. They're also known as zeros. They're also known as solutions. So whenever I say solve or find the root or find the 0, it's just finding the x-intercept, essentially. Okay. It's where the polynomial is equal to 0. Now, if you notice with this one, there are 3 zeros. 1, 2, 3. Okay. If you shifted this graph up, you can make it where there's only 1. Oops. Hold on. Let me show you. So say I did something like, here, let's make this positive. Let's make this a 3 and this a 1. Oops, let's make this minus. There we go. Just so it has some flavor. All right. If you notice, it goes up, down, then up again. And there's 3 solutions here. Okay. But what happens if I shifted this up like that? Oops, let's do that. Now, if you notice I shifted it up, now it lost 2 of the solutions. It only has 1 solution. Okay, those other 2 solutions do exist, but they're complex. They're imaginary. We're not going to deal with that in 2.1. We'll deal with that in 2.2. But I just wanted to show you that technically there's 3 solutions to this, but since there's only 1 that's real, you have to find the other 2 that are imaginary. That's with the I, if you remember from the previous unit. That's why we studied that stuff in the previous unit, because we need it for this unit. Okay, so there are still 3 solutions. It's just that one of them is real, the other ones aren't. Now, if I got rid of that 1, you could see that now there's the 3 solutions. It is impossible to get 4 solutions out of this. Okay, the graph would have to come down again, and the only way to get the graph to come down again is if you make it x to the 4th. Okay, something like that. Well, I think you have to. There we go. So now it has. Oops, hold on. Let's do +1. Oops, let's do -1. Plus 0.2. And make it so there's 4 solutions. There we go. So now there's a solution here, 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 and here. So now there's 4 solutions. But I had to make it x to the 4th to be able to make it so there's 4. You need that W shape, essentially. Okay. Are there any questions on what I'm going over here? The main thing you have to know is whatever the degree is, that's how many solutions there are. And the number of turns can help you find the degree. Okay, so right here, there's 1, 2, 3 turns. If there's 3 turns, that means you could have the max to be 4 for the degree. If the degree is 4, then there's 4 solutions. All right, complex pairs, complex roots always come in pairs. I'm not going to worry about this right now. I really probably shouldn't have gone over it yesterday because we're not even there yet. This is more like a 2.2 kind of thing. So I'm actually going to ignore it. Actually, I'm just going to ignore them for now. I'll use them for 2.2. All right, here's a breakdown of the entire unit just to kind of see where we're at. So hopefully you did the practice problems. You realize they weren't that difficult, even though I made the lecture yesterday a little bit difficult because I was talking fast and going over stuff that I thought you knew already. But hopefully when you did the practice problems, you realize they weren't actually that bad. The videos should have helped. So that was 2-1-1. It was x-intercepts, y-intercepts, the degree, and the number of turns. Oh, and the leading coefficient, whether it's pointing up or pointing down. So that was 2-1-1. 2-1-2, again, we're only going to do 5 problems today. It's about multiplicities of zeros. And multiplicity is just, it basically means like a twin or a triplet or a quadruplet, that sort of thing. So that's what multiplicity means. So there's going to be twin zeros. Like, for example, you can have 2 solutions that are x equals 1. And you would say the multiplicity is 2 because there's 2 of them. It'll make sense once we go over it. Okay, so polynomial graphs, the stuff we went over yesterday. So here's a review of the stuff we went over yesterday. We went over leading coefficient sign, whether it's a positive or a negative, it tells you where it's pointing as you go left to right. Okay, if it is positive, it's going up to the right. This is positive because it's going up to the right. This one is negative because it's going down to the right. Okay, positive, negative. This one is going positive to the right, so that's positive. This one's going negative to the right, so it's negative. Okay, it's pointing down as well. That shows you that. These 2 graphs, same thing. It's positive if it's going up to the right, negative if it's going down to the right. So if you forget that, then I would write that down in your notes because then when you're taking the test, you can use your notes. You can see that. Mr. Ozarka said if it goes to the right and up, it's positive. If it goes to the right and down, then it's negative. Okay. Okay, the next thing we went over is the lowest possible degree. You have to know how to calculate the lowest possible degree. You just take how many turns there are and add 1. Okay, we already went over this in the very beginning here, but I guess I'm just going over it again. This one has 2 turns. 1, 2 turns. Because it has 2 turns, it's x to the 3rd. It could be x to the 5th or x to the 7th, but the lowest possible one that we know for sure is x to the 3rd. Okay, this one right here is x squared because there's 1 turn, and you add 1 to 1, it's 2, so it's x squared. This one, there's no turns, so you add 1 to 0, and you get 1. That's linear, and it is linear. You can see it, that it's linear. Okay. Also, the lowest possible degree is the lowest number of complex solutions. So whatever the degree is, that's how many solutions there are. I said that already as well. Okay. Any questions on anything I've covered so far? All right. X-intercepts. You should know how to find x-intercepts. It's where it intersects the x-axis. So this one has 2 solutions. The bottom one has none. Okay, we've actually covered that exact equation in the previous unit. There are no intercepts. So because of that, those 2 solutions on the bottom, because it's quadratic, there should be 2 solutions. The 2 solutions are imaginary. That's why they don't show up on a real graph. You'd have to use an imaginary graph for them to show up. Okay, but there is still 2. You would say there's no x-intercepts, though, because it does not intercept the x-axis. But there's still 2 solutions. Still 2 solutions. All right. Oops. Yep, that's what I want. So now we're going to go over the new stuff, multiplicities of zeros. Okay, multiplicities of zeros, again, it just means there's twins or triplets or quadruplets or 5 quintuplets, whatever they're called. I don't know. All right. So multiplicity, it says sometimes a factor appears more than once. That is what multiplicity is. That is its multiplicity. So if you see this example right there, it says x squared minus 6x plus 9. Well, if you factored this, you would get x minus 3 and x minus 3. Okay. Since it shows up twice, x minus 3 shows up twice. They're twins. It's a multiplicity of 2. Okay. Now you could factor this if you want. Let me delete this. You could factor this if you want. Let me rewrite it really quick. Whoops. So you have x squared plus 6x. Wait, was that minus 6x? Minus plus 9. Okay, so that's the polynomial that we're looking at. Yeah, it was minus 6x. Now, if you wanted to, again, like I said, you can factor this. You can think, oh, what are two numbers that multiply here and add to get here? And you get x minus 3 and x minus 3. Okay, and that would be x minus 3 quantity squared. This right here, again, don't write this down. I just want your brains for right now. But this right here tells you the multiplicity. That's embarrassing. Multiplicity. Okay, it's multiplicity of 2. At x equals 3, that's the multiplicity of 2. Because if you plugged 3 in there, you would get 0 squared. Okay. Another way that you could solve this is using quadratic formula. Okay, so if you wanted to, this is a review of the previous unit, you can do negative b plus or minus the square root of b squared, which is 36, minus 4ac, this is a 1, so 4 times 1 times 9 is 36. Okay, and we're dividing this by 2a, which is just 2 times 1. Now, if you notice, this ends up being 0. Okay, 36 minus 36 is 0, so you have the square root of 0. That's where the multiplicity comes into play. Whenever you get a plus or minus 0, that is technically 2 answers. It's just that plus or minus 0, it happens to be the same thing. So you end up with 6 over 2, which is equal to 3. But you should have 2 answers. So because of this, you would have to write 3 multiplicity 2. Okay, that's if you were solving it. Okay, so if I said like equals 0 on this and you solved it, you'd say 3 multiplicity 2. So there are still 2 answers. They're just both 3. Okay, so it still does follow that rule where if the power is 2, there's 2 answers. So you'd write 3m2. Okay. Now if you wanted to, you can also solve this right here. If you notice there's 2 of them, so you would say the answer is x equals 3, but there's 2 of them, so you can write 3m2. It's the same thing. However you want to solve it, then solve it that way. One thing I do have to tell you, though, is quadratic formula always works. If you do it right, it always works. For factoring, sometimes does not work. Okay, so your best bet is always the bottom one, but, you know, that's just my opinion. Are there any questions on that? So multiplicity is when there's twins. Okay. A very interesting thing happens when multiplicity occurs. Okay. Here's that same example, me just showing you. But whenever there's a multiplicity that's even, so if you notice it says even multiplicity, there's a bounce. If you notice, it does not actually cross x equals 3. It bounces up and goes up again. That will always happen if there's an even multiplicity. Okay, let me show you some examples here. So we have y is equal to x minus 3 quantity squared. Oops, quantity squared. You can see the bounce. Okay, well, what if I change that square to a 4? There's still a bounce. See, you zoomed in, you could see the bounce a little bit better, I guess. But if I change it to a 6, okay, or an 8, but as soon as I change it to something else that's not even, like say a 1, if I change it to a 1, if you notice it goes right through it, okay? Crosses it is the correct term for it. It crosses through that 3. If it's even, it bounces. If it's odd, it crosses through. Now, I'm going to change it to 3 now. If you notice, it goes right through, but it kind of curves a little bit, but it still goes through it. Okay, it's similar to this, only that's linear through it. This one curves through it. Okay, here's 4. It's a bounce. Now I'm going to do 5. Ready? Here we go. 5, it goes through it. 6, bounce. 7, it goes through it. So long story short, again, you're going to want to know this because you're going to have to answer questions on this, is, you know, one of the questions is, is this going to be an even multiplicity or odd multiplicity just based on the graph? Well, you'd see, oh, it bounces. It bounces, it has to be even, okay? If it goes through, like this next one here, then you would say that it's odd, okay? And if you notice the multiplicity right here, it says 3. The other multiplicity was 2, so that's why it's even or odd. Okay, again, this is a lot of zookeeping. It's not a lot of writing down math and trying to figure stuff out. It's just whether it bounces or whether it goes through it. That's the main thing that we're covering here. Okay, multiplicity, it's the same thing. They're both x minus 3. You can write x minus 3 times x minus 3. There's 2 of them. This one, you can write it 3 times, x minus 3 times x minus 3 times x minus 3. Okay, no multiplicity with this one, I guess it's multiplicity 1. It just goes straight through it and it's linear. Okay, but you can still view that as a odd one because it goes through. These both go through. It's not multiplicity because there's not multiple of them, I guess. I guess you could say multiplicity 1, but it's not, you won't need to write that on like a test or anything. I did it in the notes, though. I did it in the videos that I sent you, so just so it makes more sense. This one here, so here is 2 examples of multiplicity. If you notice, they both bounce. So what is the solution to both of these? What is the answer for where it's equal to 0? What is the root? Does anybody want to unmute and tell me? Both of them have the same solution. Anybody? Okay. Well, I will go over it then. All right. It's the same rule as what we just went over. It's just a little bit trickier because it's actually on the 0. But if it said, what is the solution to this one right here at y equals x squared, you would literally just write that the answer for this, so you'd set this equal to 0. You would write the answer to this is x equals 0, but there should be 2 of these. And if you notice, it is a multiplicity because it's squared. So you would write 0 multiplicity 2. So there are still 2 answers. The 2 answers are just both 0. Okay. Also, it bounces at 0, so that tells you that it's going to have multiple. It's going to have multiple multiplicities. No, it's just going to have multiplicity. This one's a little different because if I set this equal to 0, it's going to be 0 as well. X is equal to 0, but it's going to be multiplicity 4. So they both have the same solutions, both 0, but one has a multiplicity 2, the other one has a multiplicity 4. Okay, that means there are still 4 solutions and 2 solutions for each of these, which means the fundamental theorem of algebra still holds. Okay. Here is, what did I want to show this? Oh, yeah, here we go. So if you, actually, we're going to work this problem out. Okay. I want you to actually write this one down. You don't need to draw the graph necessarily, but I do want you to write down the problem. Okay, so write down the y equals x to the 4th plus x to the 3rd. Okay, and the question is, how many solutions do we have based on this graph? Okay, well, we have one right here, and we have one right here. How many should we have total based on the equation? How many total answers should we have?
4.
Thank you, whoever said that. 4. Okay. The reason why we know it's 4 is because it's x to the 4th. Okay. The highest exponent is the degree. This tells you how many answers you have. Okay. Well, we have 2 there. So where are the other ones? Well, I'm going to show you. And the only way to really see this is by factoring this out. So that's what we're going to do. The common factor between x to the 4th and x to the 3rd, you can factor out an x to the 3rd on this. Okay, so I took an x to the 3rd out of the x to the 4th. That means there's still an x to the 1st left, And then this one, I took an x to the third out of it, so it's just going to be a 1. Okay, so if this was completely factored, it would just be equal to x to the third times x plus 1. Okay. Now, an easy way of checking this is distributing this out. Okay, so if I distributed this back into the problem, x to the third times x is x to the fourth. That's what we have here. I'm going to color code this. X to the third times 1 is this x to the x to the third right there. So factoring is basically just reverse distributive property. Okay, and that's what I just did right there. So hopefully you see that those are equal. But what's cool about doing it with factored form is now you can see the multiplicities. Okay, so what we're going to do is we're going to take this first one here and set this equal to 0. And then we're going to take this other one here and set that equal to 0. Okay. And then we're going to solve these. Okay, so this first one, you're going to do the cube root of both sides. And you get the cube root of 0 is 0. But since you did the cube root of 0, it has a multiplicity of 3. Okay. This one over here, if you subtract 1 from both sides, cancel, cancel, you're left with x is equal to -1. Now, it's got a power of 1 here, so you're only going to have one solution here. This one has a power of 3, so you have a multiplicity of 3. If you notice, it also curves but goes through it there. So that's another sign that you have some multiplicity. But now what's cool about this is you have 3 answers here and 1 answer here. So if you add those answers together, you get 4. You should have 4 total answers because, again, someone chimed in and said the degree was 4, so you should have 4 answers. So your 4 answers are 0, 0, and 0, and -1. So there's 4 answers. 0, 0, 0, because there's triplets of that, and then -1. Now, you can't really see that from the graph. I mean, I guess you kind of can because it goes through it there, and it's not a straight line, so you know that there's at least 3 there. But the easiest way to do it, to figure it out numerically or algebraically, is by factoring it. You can kind of see it from there. Okay, and if you notice, the number of answers always matches whatever the power is. So this one has a power of 3, so you have multiplicity 3. This one's a power of 1, so you have multiplicity 1. We don't write multiplicity 1, though. I mean, you can. I'm not going to mark it wrong, but you don't need to. It's kind of implied that it's multiplicity 1. Okay. So it doesn't look like there's 4 answers, but there are. It's just that some of them have multiplicity, and that's the main thing of this entire section. That multiplicity, you can have duplicates of the same answer, and it still works out to be that many answers. Okay, here we go. So this is not anything to do. It's not a problem. It's just like breaking down what a graph that's given here. So I have 2 different ones. If you notice, this one has x minus 4 squared. If you notice at 4, there's a bounce. Squared has a bounce. This one has a to the first power. It's just invisible, but it's x minus 1 to the first power. If you notice, it goes right through. Goes right through, just crosses it. This one bounces, this one crosses it. Okay, now if you compare that to the one on the right here, this one is squared. Now the x minus 1 is squared, so there's a bounce at x equals 1. Here, it's to the first power at 4, so it crosses it. Okay, I just kind of want to show you the difference between them.